I have a new course which I'm working on at the moment, which is MOSFET circuit design. So that's metal oxide semiconductor field effect transistor circuit design. I'll be concentrating mainly on the digital design, although there will be a little bit of analog design thrown in as well. Now, most of the course is based around about some simulations which I've created on a graphical calculator. So just to give you an idea or a flavour of the course, we have an example here. So I've built up a MOSFET device here, and you can see here I've got the source, which is at this side here. I've got the gate, which is this block, and I've got the drain. And it's a MOS transistor because it's got a metal surface on the top, it's got a thin oxide layer, and then it's got the semiconductor substrate here. Now the channels here for the source and drain are N type, so this is an NMOS device, and the substrate is a P channel. You can see up here we can choose the different device types, so if you click on this you can decide whether you're wanting to generate an enhancement NMOS, a depletion NMOS, an enhancement PMOS and a depletion PMOS. Now again, if you haven't done any of that design, then these terms won't mean anything to you, but all of these terms are actually explained within the course. We can also go ahead and once we've chosen the device type, so in this case here I've chosen a threshold voltage of 1, so this is going to be an NMOS device with threshold voltage of +1 volts. I can then go ahead and I can choose the gate, source and drain voltages. So for example, this case here we've got the gate voltage sitting at 5 volts, we've got the source voltage sitting at 0 volts, and we've got the drain sitting at 1.5 volts. So after we've chosen those, we can go ahead and we can choose the values for our width and length, and here's the width and length ratios here. So we've got a value here of 17 and 2, so let's put that down to say a value of 10. So say we've got a value of 10 and 2 here for the width and length, and you can see that in here as well we've got the rest of the terms are modelled here. So we've got our beta n and beta p, we've got our mu n and mu p times c tox, width upon length. So all of these process values are included within the simulation. So don't worry if you've not seen that before, this is all explained in the course. You can go ahead after you've put all your values in and you can look at the actual current equations that you get for those different voltages, and this is the different current equations that you're going to have here. You're going to have an equation which is in the linear equation, you're going to have a saturation equation for the current, and you're also going to have a cutoff equation, and you're going to have that for both the NMOS and the PMOS, and you're going to have the actual values here. So we'll see this working just in a second, and then here's just the device build. So that's how I've physically built up the device. There's nothing very interesting in that there. That's all just simply the lines that you see. So let's go in and we'll have a wee look at an example here. Let's say, for example, we went into this gate, source and drain voltage section. Now watch what's going to happen here whenever I change the value for the drain voltage. So if I increase the drain voltage, you can see here that you've got this little line here that's going to move up and down. So what this little line represents is the depletion region underneath the semiconductor. So this tells us how thick our N channel is going to be between these two N type source and drain. So this is going to tell us how much current, this is going to determine how much current is going to flow. So for example, if I was to change this VDS, the VD, and if I was to make it a value smaller and smaller, you can see here on the right hand side, I'll just move it over just a little bit so we can see it a bit better, but you can see it on the right hand side here. We've got this thing here, it says linear, and it's got the actual current value. So if I was to change this drain voltage, you see that at the moment we're actually on the linear portion of the current. So the current that flows through here is going to be linearly dependent on the drain source voltage. And you can see here that as we change this voltage, the actual thickness of the depletion region is going to decrease at one side. So you can see that decreasing value here. And as we increase this up further, we're going to hit a particular point here. So at this point here, we're going to have a pinch off will occur. So we're going to have a linear range is going to go into the saturation range, and we can see that just dropping here and jump, and you can see it jumps into saturation. And the saturation, the model we've have is a simple first order model, so it means that the current is going to just remain fixed with respect to the drain source voltage, and you can see we get that. And in that instance here, we've got cut off appearing at a particular distance along here, so pinch off occurring at a certain point. So this allows us to model the transistor in first order equations, and it gives us a good understanding, a good feel for what happens whenever we change or adjust the gate, the source and the drain voltages. And from this it's easy, or a lot easier to understand exactly how our MOSFET works. So this is just one part of the course, and the course also covers some of the device physics, and we're also going to move on and mainly look at the digital circuit design. Now, the reason for me working through this course is I have a suite of courses round about computer science. So I've got a course on designing a CPU, and I'm working through a course at the moment on designing a floating point unit. Now, I will be joining these courses together to create a 16-bit CPU with a floating point unit, but the point is that we want to be able to take this and we want to be able to produce the actual CPU and the floating point unit, and we want to be able to produce it in a CMOS technology. So we want to be able to actually build it and lay it out as if it was a proper chip, and that's what I'm working towards with this suite of courses. So I'll produce a few other videos as I work through and I get more of this course completed. It should be another 2 or 3 weeks before the course is fully completed and available. So thank you for listening. I'll get you on the next video. Goodbye.